Now that we have our ALUs sorted out, we'll build the RAM and the memory address register just below here, the counter and the clock module. And this first part here, this module just below, this will be the RAM and the logic to control it, read and write from the RAM. And this part here on the bottom, later on we'll build the memory address register. I'll show on the schematic how I intend this to work together. This here is the schematic for the RAM and the memory address register. We'll start here on this part that shows the data lines connecting the bus to the RAM, static RAM chip. This is a 6264 RAM chip, and it works the following. There's a main bus interface here, the 74LS245, that connects the bus to this internal bus that goes to the memory chip, and an intermediate logic here, also a bus transceiver, the same 74LS245 that can write to this bus according to those dip switches up here that are connected to 5 volts and the resistors to ground. So normally this here is all zeros going into this transceiver, and if we turn on any of these switches, we send a logic 1 to the transceiver. And this should work with a logic that I'll just show the following way. If the RAM is being read or written to from the bus, this chip here, this transceiver, will be active, we will enable it. And the direction that we will allow the information to flow will be controlled also from the logic. So if we are reading from the bus, it will be from B to A, and if we are outputting to the bus, will be A to B. So this logic here will integrate to the rest of the logic. But this is the first part. The second transceiver here works the following. The direction is always from B to A, so no need to control that. So we'll ground the pin 1. We'll always have the information flowing from the switches to the bus, to the internal bus here. And this chip enable, will only enable when we are programming when we're manually programming the RAM. And of course, this logic should also work in the way that this transceiver here will never be active as this one is active, and vice versa. They will only either one will be active. But not only that, because we need more logic, depending if we are manually writing to the memory, or manually reading some value to check what we have inside there. So we also need to enable or disable this regardless of this last one being disabled. And this logic that I'm just talked about is this one here. This part, this is the 74LS157, is a multiplexer, and it will be part of this logic. It has 4 outputs, and each output goes to one of these parts we need to control. So the first output here goes to the chip enable from the first bus transceiver. The second output goes to the second bus transceiver. Then we have this output here, third output, goes to the output enable from the RAM chip, and the last one here goes to the write enable from the RAM chip. And we can select then from each output has a selection, either 0 or 1 on the inputs. And so we implement the logic in a way that we can the selector here will be just a switch that we can flick between 0 and 1, and meaning 1 meaning normal operation run, and 0 being program, manual program. And this logic here should take care of everything that we need in terms of enabling each transceiver, the direction of the transceiver, enabling or the output from the RAM, or disabling it and pulsing the right enable pin. I think it's easier if I explain this logic here in another software, which is the Logitsim, and we'll do that just in a bit. I want to explain before that. I want to explain about the switches here, what we can do. So the logic here that we'll explain in a bit consists on monitoring some of the control lines that will come from the control logic. So the lines are RAM out, RAM in, and the clock signal, which actually doesn't come from the control, but anyway. And we will have not only the program switch, we'll have two push buttons. One that is show, that if we in manual mode we click this, and then whatever is in the address will be shown to us on the by the LEDs connected directly to the chip. And we have a right push button to write whatever we have selected on the dip switches to the particular address in RAM. And this right switch also has some capacitor here and a resistor, just to pulse the right enable pin, as well as the clock has a capacitor in series with a resistor to ground for it to transform the clock, the square wave of the clock, in just a positive pulse from the clock that we need to write on our RAM. What else we got here? It's the other part of the circuit is the memory address register, which is way more simpler to explain. It just consists on an 8-bit register, the 74LS377 that we already used on our registers, and it's directly connected to the bus, and we either also enable it with the memory address register in, or we can not enable it and input manually one address using the dip switches. And the way this is connected to the address lines of the RAM chip is again through these multiplexers, the 74LS157, only two of them, that will select either the address coming from the register that came from the bus, or the manually programmed address on the dip switches. And so the same selector here, the pin number 1 that selects the input, also is connected to the program switch that I just showed. So it's the same principle here, much easier to explain, because there's no output address output from this part. It's just inputting either from the bus or from the manual switches. And at last, what we have here is one address line, an extra address line that we'll be using, a 9th address pin from the RAM that will tell us if we are writing or reading from the program memory or normal storage memory that the programs will write to. This will have this division here. We have a part of the memory that's exclusive for a program and a part that's for data. And the control logic can control this from this program memory in here, this output, this input low. And we have a NAND gate that also connects to the program switch that is also output low. So in effect it's an OR gate if the inputs were positive logic. that tells us either if we are programming through manually programming, or if the control logic is accessing the program memory. Then we'll have this line here enabled, and this last address line here, address 8, will tell us, well, we are then writing to the other part of the RAM and to the program part and not the data part. Okay, that's it for the schematic. I'll then show you how about this logic here, how it's supposed to work. So as I said, for this part here, I've implemented that same logic on this program, the Logicin, so we can see how this is supposed to work. We can better understand the signals. We have the inputs here on the side and the outputs here on this side, and we have then the direction from the first bus transceiver. We have the first bus transceiver enabled that I call here chip enabled bus. We have the second bus transceiver enable line here that I call chip enable switch, which is connected to the zip switches. And we have output low write enable, output low output enable. From the inputs we have input low program, RAM out, RAM in, the push button show, push button write, and the clock. So let's then simulate something here. Let's not be programming, so we're not programming, and we are, well, right now doing anything. That's no RAM out, no RAM in. So if the clock pulses, absolutely nothing happens on the outputs, and that's what we want it to be. Everything here is disabled. The chip, the first transceiver is disabled, the second transceiver is disabled, the write enable is disabled, and the output enable from the chip is disabled. Great, that's what we wanted. Direction doesn't matter, the chip is disabled anyway. And okay, that's good. So let's do something. Well, let's just test this. What if I click anything here? Well, we see that nothing happens because everything regarding these two buttons here are connected on the side of the multiplexer that is disabled. So great, no need to worry about this now. So let's just focus on the lines here on the clock. Suppose we have them RAM out. We select. We want the output, the contents of the RAM to the bus. As long as it's enabled, it's a 1. So we set the direction from A to B. That's what we wanted the direction to be, from the memory to the bus rate. We also enabled that transceiver. Chip enable bus is output low is enabled. Great. We are not selecting the switches. Good. We are not writing, and we are outputting from the RAM chip. Good. That's exactly what we wanted. And if the clock pulses here, nothing happens. That's exactly what we needed. Great. Let's try now the RAM in. Well, on RAM in, while not programming, we want the direction to be the opposite, from B to A, so a 0 on the direction pin, which is what we got here. Good. The chip enable from the bus is also enabled. Excellent. The switches are disabled. Good. We are not writing at the moment, and we are not outputting. Okay, but as soon as the clock pulses, we can see that the write enable from the RAM chip also pulsed. Let's just keep this on for sake of the example. So we have then write enabled that will be then writing to the RAM whatever is on the bus. All right. Let's then test while we are not programming, and while we are programming. So we just turn this off, and while on this mode, on the manual programming mode, no matter what happens here to RAM out or RAM in, will influence the outputs, because it's everything connected to the part of the multiplexer that is disabled. So again, no need to worry about what's going on the control logic. which is exactly what we needed. And we also leave this right here normally as a 1, since it's a push button, and I've programmed it to be logic low. And the reason for this being logic low is just to save some chips. That's saving the need to add an inverter here. But we could do whatever we wanted. Okay, so nothing is happening now. I'm not pressing any buttons. The clock is pulsing and nothing is going on. And that's it. That's what we wanted. So nothing's going on. What that means that the bus transceiver to the main bus is disabled, and we have our dip switches transceiver enabled. So whatever we input to the dip switches is being also reflected on the I/O lines from the RAM chip. But we are not writing to it, and we are not outputting from the RAM chip. So whatever we select on our dip switches will be shown on the LEDs connected to this lines, to the I/O lines of the RAM chip. So we will know whatever we want to program will be shown on the LEDs. They will reflect whatever we put on the dip switches. And as soon as we click on the push button that says write, that we have actually a post, but for sake of this example here, I'll leave this just on for a while. So if we write, on this exact moment, we see that the write enable pin also went low, and thus whatever was configured on the dip switches got read into the RAM. Excellent. And in this situation, if you also click on the show button, if we hold to it, so let's just click it, then momentarily we disabled the switch that comes from the dip switches, and we enable the output from the RAM chip. So the LEDs will show whatever is written on this particular address from the RAM chip. It is important to disable this transceiver here, from the dip switches, or else we could cause some short circuit between whatever the RAM wants to output and whatever is selected on the switches. Excellent. And in this situation, we can also have some user proof here. If we're holding to the show push button and in the same time we for accident or anyway we pulse the right pin, let's do that. If we pulse it, then we will disable the output from the RAM chip, and we will write whatever is on the dip switches. So it's kind of a foolproof here. We cannot damage anything by pressing these two push buttons together. It won't cause any incompatibility. We will just write whatever on the dip, or whatever is selected on the dip switches, which is what we want to do when we post the right button. So I guess this is all right. And on these situations, again, no matter what the clock makes, it's connected to a non-used part of the multiplexer. So that's it for this logic. You might be wondering why I've used this gate here, for example, is two inverters and then an AND gate and another inverter in front of it. Well, I could have as well used an AND gate directly here, or an OR gate that would substitute this four logic parts here, the gates and the inverters. Well, yes, I could have done this, but this way that I've implemented, I've managed to use only two chips out of the multiplexer, because each inverter chip has 6 inverters. I'm only using 4 of them here, and each NAND chip has 4 NAND gates, and I'm using 3 here, and I got 1 extra that, if you recall, I also used on the rest of the logic to enable the program memory part of the chip. So I guess this was the the most optimization I could do using only these two chips, the one inverter and the one NAND gate. It could have been done easy, with a more straightforward way, with AND gates, on one AND gate here, for example, and then the inverted for this part, one OR gate to substitute this whole part here. But we would have needed to use more chips in the end. Something I wanted to mention that I forgot is that the clock input to the right pin of the RAM chip, this clock input here, I called it clock 2, and it only means that it's coming from another inverter on our clock module, because since we're feeding it to this capacitor in parallel to the resistor, I don't want to also mess up the rest of the clock inputs from the computer. So I'm using one dedicated clock signal. Okay, I guess that's it for the moment. Well, let's start with our build.